Have you ever wondered what happens when a military loses its eyes and ears in a split second? What if the invisible shield protecting a multi-billion-dollar aircraft carrier suddenly shatters, not from a missile, but from a silent pulse of energy? Welcome to the invisible battlefield. Today, the greatest threat to modern militaries is not a kinetic explosion. It is the overwhelming chaos of the electromagnetic spectrum. For decades, traditional electronic warfare ruled the skies. But it has hit a fatal wall. It is too slow, too rigid, and easily outsmarted by modern frequency hopping radars. Militaries are facing an impossible problem. How do you jam an enemy radar that changes its signal 1,000 times per second? The answer is a radical leap in technology. A leap that takes the human out of the loop and hands the control over to an artificial intelligence. This is cognitive electronic warfare. To understand the sheer magnitude of this shift, we first need to dissect the legacy counterpart. Traditional electronic warfare operates on a brute force paradigm. For decades, its strength lay in sheer reliability and massive power output. When an aircraft like the EA-18G Growler entered a combat zone, its primary job was to detect hostile enemy radar signals and blind them. But let us break down exactly how this legacy system operates in a sequential flow. First, the aircraft's sensors passively ingest radio waves from the surrounding environment. Second, the system digitizes these signals and compares them against a hard-coded threat library. Think of this library as a static dictionary of known enemy radar signatures stored on physical memory drives. Third, a human operator must look at a screen, recognize the match, and manually select a jamming technique. Finally, the system transmits a high-power barrage of interference to blind the enemy radar. This process worked flawlessly against older, predictable threats. But today, it creates a catastrophic vulnerability. The legacy architecture suffers from severe latency. Modern adversaries now use advanced radars that change their operating frequencies thousands of times per second. By the time the legacy system matches a signal in its dictionary and the human operator presses a button, the enemy has already shifted to a new frequency. The jamming misses the target entirely. Furthermore, this legacy system is completely blind to novel threats. If an enemy turns on a brand new radar that has never been recorded, the signal will not exist in the onboard dictionary. The legacy system will not recognize it, leaving the aircraft completely exposed to surface-to-air missiles. This creates a massive economic and structural conflict. Militaries are pouring hundreds of millions of dollars into maintaining massive electronic warfare pods that are fundamentally limited by static software and human reaction times. They burn excessive aviation fuel to generate brute force barrage jamming, which often creates so much collateral interference that it blocks friendly communication network. The legacy approach is a massive financial drain that is losing the physics battle against speed. We need a system that thinks for itself. A system that does not rely on a dictionary but learns in real time. We are entering the era of the machine mind. Enter cognitive electronic warfare. This next-gen weapon entirely rewrites the rules of spectrum dominance. It strips away the static threat libraries and removes the human bottleneck, replacing them with a highly advanced artificial intelligence architecture. The insights driving this technology are rooted in machine learning and neural networks. Instead of relying on a rigid dictionary of known signals, cognitive systems understand the raw physics of the electromagnetic spectrum. Let us explore the structural design and mechanical improvements that make this possible. The hardware abandons older traveling wave tubes in favor of active electronically scanned arrays built with gallium nitride solid-state transmitters. Gallium nitride is a highly durable semiconductor material. It allows the system to generate immense voltages and project focused beams of radio frequency energy without melting down. These arrays are governed by tightly packed clusters of custom processors running deep neural networks. These processors are liquid-cooled and require heavy rare earth magnets, specifically laced with dysprosium, to handle the extreme thermal and magnetic loads. Without these specific materials, the ambient heat generated by the computing power would instantly destroy the hardware. Now, let us compare the new operational kill chain directly against the legacy flow. The difference is staggering. Step 1 remains similar. The cognitive system continuously vacuums up terabytes of spectrum data from the environment. But step 2 is where the revolution happens. When the sensors detect a hostile radar, they do not check a database. Instead, the deep neural networks instantly analyze the physical parameters of the signal. They map the bandwidth and the pulse repetition interval in real time. The system categorizes the threat based on its behavior, successfully identifying brand new, completely unknown radars that have never been seen before. Step 3 introduces autonomous strategy formulation. Using a machine learning model called Q-learning, the artificial intelligence predicts the enemy communication pattern. It dynamically formulates a custom jamming response. Step 4 is the active execution. The software-defined radar steers concentrated energy directly into the enemy receiver with pinpoint precision. This entire operational flow, from initial detection to active jamming, occurs in a fraction of a second. Algorithmic response times have been recorded at speeds as low as 1/10,000th of a second, which is completely invisible to human perception. When the enemy radar attempts to evade the jamming by hopping to a new frequency, the cognitive artificial intelligence tracks the shift instantly. Even if the hostile transmitter changes its signal thousands of times per second, the neural network predicts the exact destination frequency. It dynamically alters its own transmission frequencies, beam directions, and waveform shapes to match the enemy step for step. It is a continuous, autonomous cycle of evasion and suppression that requires absolutely zero human intervention or manual targeting adjustments. This completely solves the legacy flaws. The latency bottleneck is destroyed by computational speed. The vulnerability to unknown signals is eliminated by behavioral learning. The collateral damage caused by brute force barrage jamming is replaced by surgically precise interference that leaves friendly networks untouched. And economically, it inverts the cost of warfare. While adversaries spend millions of dollars firing kinetic missiles, the cognitive system neutralizes their targeting data using zero-cost photons. The enemy is effectively blinded by an invisible, thinking machine. But does this futuristic artificial intelligence actually work outside of a computer simulation? The defense sector has already provided the undeniable answer. This is not theoretical science fiction. The shift from laboratory prototyping to active fleet integration has already occurred, backed by extensive testing and massive procurement budgets. For years, the Defense Advanced Research Projects Agency laid the groundwork with experimental algorithms, proving that neural networks could process chaotic spectrum data instantly. But the true operational resolution arrived recently. In December 2024, the United States Navy achieved a massive milestone by officially declaring initial operational capability for the next-generation jammer mid-band system. This declaration meant the weapon was officially certified as ready for real combat operations. The fleet received a direct preview of these high-end capabilities when Electronic Attack Squadron 133 deployed with the system aboard the aircraft carrier USS Abraham Lincoln. This marked the very first time the next-generation jammer was used in both active deployment and combat environments. The system successfully demonstrated drastic increases in power output, target flexibility, and surgical jamming techniques, proving the absolute superiority of software defense superiority. Following this maritime deployment, the defense sector accelerated the integration of artificial intelligence directly into the sensor architecture. In February 2025, Raytheon publicly announced the successful flight testing of the cognitive algorithm deployment system. This test integrated advanced machine learning models directly into radar warning receivers. The hardware and cognitive processing capabilities were mounted on an F-16 aircraft and flown through rigorous evaluations at a test range near Tucson, Arizona and Lake Tucson. The results were definitive. The cognitive architecture successfully sensed, identified, and prioritized threats autonomously. It proved that artificial intelligence can rapidly enhance aircrew survivability by making split-second decisions in highly contested airspace. Looking toward the exact future deployment timelines, the defense industrial base is rapidly scaling full-rate production. Procurement targets are aggressive and heavily funded, moving past the initial development phases into billion-dollar acquisition pipelines. Following the successful initial tests, the Department of Defense authorized extensive low-rate initial production contracts, committing hundreds of millions of dollars to build massive stockpiles. By April 2026, the technology had expanded to allied nations, with the Royal Australian Air Force officially taking delivery of their very first next-generation jammer. Over the next few years, the primary engineering focus will shift towards software upgrade blocks and hardware miniaturization. By 2027, the defense sector plans to roll out the mid-band expansion upgrade, extending the frequency range to counter even more complex adversary threats. Engineers are heavily focused on shrinking the liquid cooling infrastructure, aiming to overcome strict size and weight constraints. This future miniaturization will eventually allow cognitive electronic warfare payloads to be deployed not just on heavy aircraft, but on thousands of autonomous drones swarming ahead of the missed drones. The invisible battlefield has fundamentally changed, and the cognitive machine has already won the first engagement. The rapid evolution of cognitive radar systems highlights a deeper narrative about raw engineering grit. Developing artificial intelligence that can survive the extreme thermal loads and violent vibrations of supersonic combat requires brilliant mechanical design. It takes profound dedication to turn rare earth elements and raw code into a functional weapon system that protects the lives of pilots every single day. We want to know what you think. Should we cover more stories about the relentless engineering grit required to build these modern marvels? Or would you prefer we dive into another complex future technology scenario? Leave a comment below with your preference. We know exactly which next-gen weapon the channel should cover next. Your feedback directly shapes our future content. Do not forget to like this video and subscribe to the channel to help us grow and keep bringing you the hard facts on the future of warfare.